All right, today we're going to peel back the curtain on one of the most important, yet totally invisible technologies in our lives: elliptic curve cryptography. This is the unsung hero that secures everything from your texts to your banking, and we're going to break down exactly how this really elegant piece of math actually works. So, let's start with a question. Kind of a puzzle. How is it that this little low-powered device in your pocket can pull off security that would have made a supercomputer sweat just a couple of decades ago? The answer? Well, it isn't just about faster chips. It's about much, much smarter math. And here it is, right here, in a nutshell. On the left, you've got a traditional RSA key, which needs to be over 3,000 bits long to be considered secure. But look at the right. An ECC key gives you that exact same level of security with just 256 bits. It is way smaller, way faster, and so much more efficient. But to really get why this is such a game changer, we have to look at the problem with those big, bulky keys in the first place. Yeah, to appreciate the new, you've really got to understand the old. For decades, the king of the hill in public key cryptography was RSA. And look, it was a brilliant system, but as our security needs got more intense, it started to show its age. And honestly, it came with some serious baggage. The whole idea behind RSA security is a pretty simple principle. It's easy for a computer to multiply two huge prime numbers together. But if you take that final product and try to work backward to find the original two primes, well, that is incredibly difficult. That difficulty, that's the lock on the door. But here's the catch. As our computers get faster and faster, they get better at cracking that problem. So to keep RSA secure, the keys just have to get bigger and bigger and bigger. And this creates a huge burden. We're talking slower operations, more power being drained from your battery. It's a system that's just not practical for the billions of tiny, low-power devices that pretty much run our world now. Something new was desperately needed. And that new approach came from a completely different corner of the mathematics universe, first proposed way back in the 1980s. Instead of just making the numbers bigger, mathematicians turned to the strange and kind of wonderful properties of something called an elliptic curve. Now, when you hear elliptic curve, you probably picture something that looks like this: a nice, smooth, continuous line on a graph, right? It's defined by a pretty simple-looking equation, and it has some really elegant properties. But this smooth curve isn't actually what we use for cryptography. This is... yeah, looks more like someone just sneezed a bunch of dots onto the screen, doesn't it? So, what happened to our beautiful, smooth curve? Well, the secret isn't the curve itself, but the strange mathematical world that it lives in. That world is called a finite field. Think of a clock. When you go past 12, where do you go? You wrap around back to 1. A finite field does the exact same thing for the numbers on our curve. All the math is done modulo p, where p is a massive prime number. This means instead of the line just shooting off to infinity, it wraps around, and all those infinite points get squished into this finite, grid-like space. That is how we get our scatter plot, and this weird structure is what makes the whole thing work. Okay, so we've got this wild collection of points. How in the world do we turn that into a secure system? Well, it all comes down to a really clever set of rules for combining points on the curve. Think of it like a mathematical secret handshake. It all starts with something called point addition, and when you see it, it's surprisingly simple. You just take 2 points on the curve, let's call them P and Q, and you draw a straight line right through them. That line is going to hit the curve at a third spot. You take that third point, flip it across the horizontal axis, and voila! That new point is what we define as P plus Q. It's a super consistent way to add 2 points and always end up with another point that's still on our curve. So a natural question is, what happens if you add a point to itself? P plus P. We'd call that 2P. And what if you do that over and over again, say D times? That process is called scalar multiplication. You start with a known point on the curve, we call it G, and you multiply it by a secret number, D, by just adding it to itself D times. The result is a totally new point, Q. And here it is, the absolute heart of the whole thing. Doing that scalar multiplication is easy for a computer. If you have the starting point G and the secret number D, finding the final point Q is fast. But, and this is the crucial but, going the other way is practically impossible. If you only know the starting point G and the final point Q, you cannot figure out D, the number of hops it took to get there. It's a mathematical one-way street. This is called the elliptic curve discrete logarithm problem, and it is the entire foundation of ECC security. So this whole system maps perfectly to public and private keys. Your private key is just D, that secret random number that only you know. And your public key? It's the point Q that you get after doing the math. You can shout your public key from the rooftops, share it with the whole world, because even though everyone knows Q and the starting point G, they have no way of using them to figure out your secret D. So we have this really elegant math system built on a very hard problem. What does that actually mean for us in the real world? Well, this is where ECC really starts to shine, and it's why it's pretty much taken over. I mean, just look at this comparison. It's absolutely stunning. To get the same level of security that a little 256-bit ECC key gives you, you'd need a monster 3072-bit RSA key. That's more than 10 times larger. This massive difference in size has these huge consequences for performance and efficiency. That tiny key size translates directly into huge wins for us. Computations are way faster, which means less waiting around. The keys take up less storage, they need less data to be sent over a network, and maybe most importantly, they use way less power. This makes ECC the absolute perfect choice for all the battery-powered gadgets in our lives, your phone, your smartwatch, and all those tiny Internet of Things devices that still need to be super secure. And believe me, you are using this constantly, probably without even realizing it. The Signal protocol that secures apps like WhatsApp? That's ECC. Cryptocurrencies like Bitcoin and Ethereum? They rely on it to protect every single transaction. And that little padlock in your web browser, HTTPS. Yeah, that's often ECC too. It is the invisible engine of our modern digital security. But the story of cryptography is, and always has been, a constant arms race. And just as ECC came along to solve the problems of RSA, there's a new challenger looming on the horizon that threatens to break ECC itself. And that threat comes from quantum computers. There's a theoretical algorithm called Shor's algorithm, which is specifically designed to run on a large-scale quantum computer. And if one is ever built, it will be able to solve the hard problem behind RSA and the one-way street behind ECC, basically making our current security standards totally useless. Now, this isn't time to panic just yet. Cryptographers have seen this threat coming for years, and they are already hard at work building the next generation of security. The field is called post-quantum cryptography, and it's all about finding brand new, hard problems that even a powerful quantum computer won't be able to solve easily. Which leaves us with the big question for the future. Elliptic curve cryptography was this beautiful, efficient shield for the mobile era. But as the quantum era gets closer and closer, the race is on to find and standardize the next mathematical shield that's going to protect our digital lives for decades to come. What's that going to look like? Well, that's a story for another explainer.